Late?
Light.
Light? It's been light this entire week. I feel like people have realized that I've like record these now, so they just like stop showing up.
Oh yeah.
All right, let's get started. So what we're talking about this week. It's called the method of undetermined coefficients. And this is also known as the Annihilators chapter. Okay. And the whole point of this chapter then is to deal with the following. So last week, right, we talked about homogeneous diffie-qs. So we talked about PD of y is equal to 0. And so this week, then, we're going to talk about non-homogeneous, where PD of y is equal to f of x. And so we have a right-hand side now that's going to be non-zero. Okay, so that's the difference. That's literally the only thing we're doing differently. So the rest of this entire chapter is going to be talking about how we deal with this right-hand side f of x. Okay, because the homogeneous solution, that's like pretty simple to deal with. You only have so many cases. However, with the right-hand side f of x, you can run into a lot of trouble really quickly. And so this is just the first method then. The method of undetermined coefficients, just the first way we teach you on how to deal with this. It's by far the least elegant and by far one of the most useless ways. But we always start with most useless, and then we build up to better things. So we need to create a table. So I recommend putting this like on a new page. So we're going to create a table, and it's going to be the following. So on the first part of the table, we're going to have what you see on your right-hand side. And then we're going to have your annihilator that goes with it. And then we're going to have a guess of a particular solution that goes with that right-hand side as well. So this table is more or less just going to be summarizing this table here on page whatever. It's in my video as well, 524. I'm going to be summarizing this top table. I can't click that, but it's fine. So I'm going to be summarizing this top table up here. So what we're going to see is that on the right-hand side, you'll see, firstly, the most common one, or not most common, but the first type of right-hand side you'll see is going to be some constant times x to the k e to the ax. Okay. And so what the annihilator does, the annihilator essentially kills this term. Okay? And so we'll see. I won't actually like take the derivatives of it, but we'll see examples of this a little later on. But the annihilator then for cx to the k e to the ax is d minus a, and we raise it to the k plus 1 power. Okay, and remember, d is the derivative map, so we just take derivatives of the f of x guy. Okay, we'll leave the yp of x alone for now, because we'll get back to that once we actually solve diffie-qs. Because for right now, we're actually just going to be doing some annihilator stuff. So the next one is going to be cx to the k e to the ax cosine bx, or cx to the k e to the ax sine bx. Okay, so this is what happens when you have that, and then now you have cosine and sine terms. So annihilator here is going to be a little more involved. It's going to be parentheses d squared minus 2ad plus a squared plus b squared raised to the k plus 1 power. Okay. And the reason why we have this is because you can think of the roots of this equation are a plus or minus bi, right? Which is exactly what we need to kill this guy over here. So that's how we do that. Okay, and then the third the third term, or the third type of thing you're going to see, is just going to be a sum of the above. So you're just going to have like these individual terms just added with each other. And then the annihilator is just going to be the sum of the individual annihilators. Okay. Let's put these into use. So, example, right? Let's say I have the following. My examples are all over the place this week, so here we go. So number one is just find the annihilator. All right, so number one, we're going to have f of x is equal to 2e to the x minus 3x. Okay, so what case do we have? Well, this is we have a sum, right? Well, this is a subtraction, but really, right, subtracting is adding negatives. And so we have a sum of the above, so we need to look at each individual piece term-wise. So we look at 2e to the x. Okay, what is 2e to the x? We go back up here to our table, and 2e to the x looks a lot like this first case, right? There's no cosine or sine term. So, yeah, so that's what it is. It's really c, right? It's some constant times e to the x. We can see that k is equal to 0 and a is equal to 1. Right? E to the x is e to the 1x. And then k is 0 because there's no x term. And so then the annihilator is going to be d minus a to the k plus 1. So d minus a to the k plus 1. But k is 0, a is 1. So this is just d minus 1. All right, next term, same thing, negative 3x. This is a constant times x. So what has changed now, k is equal to 1, but a is 0, right? Because e to the ax, if a is 0, you're raising e to the 0 power, and the e to the 0 is 1. So we just don't see the e. All right, so if you don't see an e, that just means a is 0. That's what that means. Okay. So again, we use the same thing. We use d minus a to the k plus 1, except now a is 0, k is 1, and so we get d squared. And then since this is a sum of terms, then we want to sum the individual annihilate, or, ooh, I said sum. This is product. My bad. Product of the individual annihilators. Product. And so we'll get then a of d is equal to d squared times d minus 1 as the solution. Okay, any questions? Yeah.
The f of x would be on the right-hand side of?
It's always right-hand side, okay. Yeah. If you look at up here, PD of y is equal to f of x, yeah. Okay. Number 2. Okay, so we'll do f of x is equal to e to the negative 3x, 2 sine x plus 7 cosine x. All right, so FOIL this out, 2e to the negative 3x sine x plus 7e to the negative 3x cosine x, right? So we have a sum again, and you'll want to take this term-wise. So this is 2e to the negative 3x sine x, all right? That looks a lot like a constant e to the ax sine bx, right? And so if we go up here, that's going to be the second case, right, where k is 0. So we have k is 0. So I guess, yeah, whatever. So k is 0, a is negative 3, and b is 1. Okay, so we want to use this annihilator, d squared minus 2ad plus a squared plus b squared raised to the k plus 1. And that's just then d squared plus 6d plus 10. Likewise, 7e to the negative 3x cosine x. You get c e to the ax cosine bx, but k is still 0, a is still negative 3, and b is still 1. So what's going to happen is that when you use the annihilator, you're just going to get the same thing. And then you're just going to get the same answer. So this is equal to d squared plus 6d plus 10. So here's the thing, right? So if we write AD down, we have d squared plus 6d plus 10, but we really don't have to multiply them by each other, right? Because we're killing the same thing. You'll notice since the a and the b are the same thing, and the k's are the same thing across all three, across both of these annihilators, or both these terms, we get the same annihilator for both terms, which means that the same annihilator will just kill both terms. Right? So there's no point in multiplying them together. It'll still work. I mean, it'll still kill both terms. But the same, like d squared plus 6d plus 10, we're just going to kill both of them anyways. Okay? So the annihilator then, if a and b are the same, you just take the highest power of k. All right? And in this case, k is 0, so that's the highest one we take, which is going to be d squared plus 6d plus 10. So what I mean by that is that if this term was like d squared plus 6d plus 10 to the 7th, right? But this term up here was still d squared plus 6d plus 10, my annihilator would be this guy to the 7th. I would just take the highest power annihilator if they shared the same a and b's. But in this case, the highest power is just the regular guy. Okay, any questions on annihilators? Okay, so what are they used for? Well, they technically should help you find the particular solution in guessing diffie-qs, but we almost never end up using them anyways, so I guess we just did this for like a homework help. So let's move on to then solving diffie-qs with f of x not equal to 0, right? So what are we going to do? So first of all, let's fill out this table up here. Okay. So you have yp of x, right? And so you have f of x on the right-hand side. And so what do you guess for yp of x? So if you have c x to the k e to the ax, your guess yp of x should be e to the ax times a naught plus a1x plus a2x squared plus dot 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 plus akx to the k. So it depends on what power your k is. That tells you how many terms are in your guess. Okay? If you see this guy right here, the cx to the k e to the x, then you'll guess yp of x is equal to e to the ax times, all right, this gets a little annoying, a naught cosine x plus b naught sine x plus a1x cosine x plus b1x sine x plus all the way up to ak x to the k cosine x plus bk x to the k sine x. All right, and then you have a sum of the above. So this usually won't happen in these types of problems, so I don't think you have to worry about these too much. So first of all, don't worry about this too much. And I'm not even sure what the correct answer is supposed to be, but I think intuition would say that since the solution of diffq is a vector space, it should be closed under addition. So I'm guessing this is just going to be a sum of the above yp's. But you'll never see this, sum of individual yp's. You'll never see this, and the book doesn't use it as a case either, right? So this table in the book that we're summarizing right now, you see that there's really only two cases. They don't give you that sum case, so you don't have to worry about that. And the other thing is that if you do have a nasty right-hand side that includes a bunch of sums, you probably don't want to be using this method anyways. So I'm going to put a question mark here. Okay, so let's look at this in action. So what kind of problems do you usually get? Well, you'll usually get just the following. So one is just determine the general solution. To some differential equation. So in this case, y double prime minus 9y is equal to 10 e to the 2x. Okay, so solving diffq is a very formulaic, like step-by-step approach, and like the only way you can mess up there's really only two places that you'll mess up. So step one is the following: is to find the homogeneous solution yh. So what we're going to do is we're going to take y double prime minus 9y, and we're going to set it equal to 0, and we just have to find the solution to this. All right. So this is what we did all of last week, and this should be nothing new. So I'm going to do it quickly. D squared minus 9 applied to y is equal to 0. D is equal to plus or minus 3, so yh is equal to c1 e to the negative 3x plus c2 e to the 3x. Does anyone have any problems with that? Okay, so that should be straightforward. So this is where the new stuff comes in. Step two is we want to guess the correct yp of x. All right, and I think I said on Piazza that to some question that like a lot of diffqs was just educated guessing. This is where it starts. So, all right, so now what we do is we look at the right-hand side. It's 10 e to the 2x. All right, so we go up here to our table. All right, and we say, okay, 10 e to the 2x. All right, what does that look like? It looks like this guy. So now then we have to go over here, and we have to be like, okay, k is 0, right, in 10 e to the 2x. So that means we only need like the a naught term. Okay, and then what else? Then, okay, a is 2, and that's it. So it looks like my guess will be a naught e to the 2x. So I go down. Yp of x is equal to a naught e to the 2x. All right, and to simplify things, I'm just going to drop the naught so we don't have to write like this subscript over and over. So I'm just going to say some constant a times e to the 2x. All right, and again, it's based on the right-hand side, not the left-hand side, right? It's based on the right-hand side f of x. So guess the correct given right-hand side f of x. Let's write that in. Step 3 is we want to plug this in, plug yp of x back into the original equation. Diffq. Okay. So what does that mean? That means that, okay, so you see y double prime minus 9y is equal to 10 e to the 2x. I'm literally plugging y into that equation up there. So we have y double prime minus 9y is equal to 10 e to the 2x. Okay. And then yp of x, right, is equal to a e to the 2x. So now, what's the highest order differential, like the highest order derivative that I need? 2, right? Because I have a y double prime, so we just have to take derivatives of this guy. So yp prime of x is going to be 2a e to the 2x. And then yp double prime of x is equal to 4a e to the 2x. Okay, now we just plug all this back into my equation. So y double prime, right, is now 4a e to the 2x. So this is going to be 4a e to the 2x minus 9 times y, but y is a e to the 2x, is equal to the right-hand side 10 e to the 2x. And up here, we want to say we solve for the constants. But after you do this a lot of times, it becomes immediately clear what you're supposed to do. So, okay, so now what you get negative 5a e to the 2x is equal to 10 e to the 2x. All right, we can solve for my constant a now. A is equal to negative 2. Right? And what does this mean? This means that then for my original solution, for my original guess of yp of x, right, a is really negative 2 e to the 2x. So that's really what my yp of x is. Right? And so we'll write it again down here. So this implies that yp of x is equal to negative 2, not a, negative 2 e to the 2x. Okay? Step 4 is then to write the general solution, which is y is equal to the homogeneous plus the particular. All right, we solve for homogeneous in step 1. Now we solve for the particular, which we got in step 3. So y of x is equal to c1 e to the negative 3x plus c2 e to the 3x minus 2 e to the 2x, right? Here is your homogeneous, here is your particular, and this is your final answer. Yeah.
What if the 3 was a 2 and then like?
We'll deal with that. Okay, any questions? All right, so again, so where are the places that people usually mess up? It's either going to be step 3 right here where you're taking the derivatives and plugging it back in the equation. A lot of algebra mistakes happen there. Okay. Another place, your guess could have just been wrong. That also happens a lot. So really the only 2 steps, if you had to diagnose like where you're doing something wrong, it's going to be these 2 steps right here. All right, let's take a look at another example. This one's going to be y double prime plus 16y is equal to, I don't know what's equal to, 4 cosine x. All right, step 1 is the homogeneous. We're going to do this one quick. It's the homogeneous, so y double prime plus 16y is equal to 0, right? D squared plus 16 applied to y is equal to 0. D is plus or minus 4i. And from last week, this tells me that yh, the homogeneous, is going to be c1 cosine 4x plus c2 sine 4x. Okay. Now what? Now we have step 2 is to guess the yp. All right. So again, we're dealing with the right-hand side. So here's our right-hand side. It's 4 cosine x. All right. So we're going to go up to the table. Here's the table. All right. 10 e to 2x can go by. We have 4 cosine x now, all right, which definitely looks like one of these guys. Okay, so what do we have? We have k is 0, a is 0, and b is 1. Okay, so if we go over here, since k is 0, right, the highest term we're going to get to is a naught and b naught. Right? So a is 0, so that means e to the ax, that's just going to be 1. And it looks like that my guess is just going to be a naught cosine x plus b naught sine x. Hold on one second. That doesn't look too correct. Okay, it's not right because I'm missing a b. I'm missing a b. So all these x's should be bx's in the cosine and the sines. Or little b's. Okay. I'm going to highlight this just to... Yeah, so that should be bx, that should be bx, that should be bx, that should be bx. These should all be bx's. It makes sense. Okay, anyways, since b is 1, we would have just gotten a naught cosine x and b naught sine x anyways. So so guess yp of x. So yp of x is a naught cosine x plus b naught sine x. And I'm just going to drop the naughts again, the subscript zeros, because they get really annoying to write when you have to do this over and over. Okay, step 3 is to plug in the original. So since yp is up there anyways, I'm just going to take derivatives now. So yp prime is negative a sine x plus b cosine x. And then yp double prime is equal to negative a cosine x minus b sine x. Okay, here's my original equation. Y double prime plus 16y is equal to 4 cosine x. And now, so you get, plugging in, you'll get negative a cosine x minus b sine x plus 16 times yp, which is this original guy, a cosine x plus b sine x is equal to 4 cosine x. This is 15 a cosine x plus 15 b sine x is equal to 4 cosine x. All right, what can you say about b? 0, right? There's no sine term on the right-hand side, so b is 0. And then we can solve for a, and you'll see that a is equal to 4/15. So then my particular solution, yp, is really just 4/15 cosine x. There's no sine term. And then what else? Step 4 is the general solution. So y of x is equal to the homogeneous c1 cosine 4x plus c2 sine 4x plus the particular, which is 4/15 cosine x. There we go. Any questions on this?
How do we get from the y double prime step on the top to one below?
Which one?
The y double prime plus by is equal to 4 cosine x, and then the step
Y double prime plus, oh, this is 16y.
Oh, 16.
right? And then I'm just plugging in my yp's into my y's.
Okay, cool.
Okay. Everyone get this fixed up here? The bx? Okay. Yeah, it's in your book. This is in your book anyways, whatever page that was, 342, something like that. 524. So that's what I'm just copying off of anyways. Okay, so now let's take a look at another case. All right, we have this differential equation, y double prime minus 5y prime plus 4y is equal to 7x e to the 4x. Okay, step 1 is the homogeneous. I'm not even going to do this anymore. I'm just going to tell you d is equal to 1 and 4. And so we'll get yh is equal to c1 e to the x plus c2 e to the 4x. So Jaden, here's one of those examples. Okay, step 2 is to guess yp. All right, so my right-hand side is 7x e to the 4x. We're going to go up to this table, and we're going to look at it for some inspiration. 7x e to the 4x. All right, it looks like a is equal to 4, and x is equal to 1. So that means I need to go all the way up until this term, right? I need to go up to the first term since k is equal to 1. Okay? So, okay, so I'll have e to the 4x times a naught plus e to a to the 4x times a1x. So, let's say yp of x is equal to a naught e to the 4x plus a1x e to the 4x. Okay. Any questions so far? Okay, this is wrong. So our table has betrayed us. Can anyone see why this is wrong? Anyone want to take a stab at why this guess is wrong?
Like the first one or a 6?
Where they're all 4s. Yeah. Yeah.
If you were to add the yp to the homogeneous solution, it would like combine with the other term.
Yeah, that's the idea, right? This guy and this guy are like the same thing, right? You have a constant times e to the 4x in your homogeneous, but you also have a constant times e to the 4x in your particular, right? So remember what the particular solution is supposed to do. It's supposed to solve the right-hand side, right? But if this particular solution is in the homogeneous, what is this term actually doing? If this term is actually in the homogeneous solution, it's actually solving the homogeneous, right? Because it's literally the same thing. It's literally a constant times e to the 4x, right? So this term right now, this a naught e to the 4x term, it's solving the homogeneous, right? It's not solving the particular solution. So our particular guess is just wrong. So how do we remedy this? Well, the idea is the following. If this term right here, right, this is a 4x, right? So this is where it went wrong. You have c x to the k e to the ax, right? That's the general form of this guy, is c x to the k e to the ax. If a is a root of the homogeneous, right, which it is, right, this 4 is a root of my homogeneous of multiplicity m. Then we have to multiply our guess by x to the m. So what's the multiplicity of 4 in my homogeneous equation? It's 1, right? It occurs once, okay? So what does that mean? That means I have to take this guy, right? I have to multiply by x to the m, but m is 1, so this is just x to the first. All right, so this is the fix. Because now what happens when I multiply that x through, right? I get the following. I get a naught x e to the 4x plus a1 x squared e to the 4x. Right? And now I don't have this problem where this guy is in my homogeneous, because it's not. All right, so none of my particular solution terms are in my homogeneous solution anymore. And that's good. Okay, and if you have complex numbers, it's the same thing. If it's like c, so for complex, if you have like c x to the k, so we'll write this down here actually. For complex, if you have c x to the k e to the ax cosine bx or sine bx, you have to look at if a plus bi is a root. So the same thing applies.
If it is, then you also multiply.
Yeah, then you also multiply by the multiplicity of that root of a plus bi. Again, this is all summarized. It's all summarized here. So up here, right, you see the modified trial solution on the top. Where's my mouse? So this part right here, the modified trial solution, this is what I'm summarizing right now.
Does it also explain in the book why that works? If you
Like why does multiplying by x work? It's kind of like the remember when we did the homogeneous thing? It was like, oh, you have multiplicity, you need to multiply by x. It's the same idea. It's that you need linearly independent solutions. Okay, so is everyone okay with this guess part? Because this is like this. So you'll never get a differential equation that doesn't have something going on with it, and so this is like a really common thing that happens. Okay. Step 3, you plug it back in. Oh boy. All right, so we need up to 2 derivatives. This is why I said this isn't the most elegant solution, because well, we need the product rule. So this first term, right? This first term becomes a naught e to the 4x plus 4a naught x e to the 4x. Okay. The second term becomes 2xa1 e to the 4x plus 4a1 x squared e to the 4x. All right, so that's the second term. Okay, so I'm going to rewrite this. This is 1 plus 4x times a naught e to the 4x. And this becomes 2x plus 4x squared times a1 e to the 4x. All right, yp double prime of x. The reason why I did this is so instead of taking the product rule on 4 separate terms or 3 separate terms, I'm only doing it twice. All right, so now you got to take the product rule on this guy. So what it is, it's the derivative of the first guy times the second guy plus the derivative of the second guy times the first guy. So this is 4 times a naught e to the 4x plus 1 plus 4x times 4a naught e to the 4x. All right, and then now the second term, the derivative of the parentheses is 2 plus 8x times a1 e to the 4x. And then the second derivative here is going to be 2x plus 4x squared. And this is 4a1 e to the 4x. All right, so like I said, ample opportunity to make a algebra mistake here. Okay, for the sake of time, I'm not going to plug this back in to the equation, but you guys understand, like, the next step, right, is you have to plug it back into the equation with all these derivatives. So what you'll get is that you'll get a1 is equal to 7/6, and you'll get a2, or a naught is equal to negative 7/9. So this is what you should get. So after some algebra. Okay? And so the important thing is to realize that, okay, this is your guess for yp of x. All right? That's important to know, that you need to change it. And the second thing is to recognize that your derivatives require the product rule almost everywhere. Okay? And the rest is just really computationally tedious algebra. So one thing that you can do to check yourself, right, is to plug this in a Wolfram alpha. So, so if you go to Wolfram alpha, right, you can literally just plug in diffie-q's into this thing, which is really nice. So, right, y double prime minus 5 y prime plus 4y is equal to 7x e to the 4x. Okay, and so here's your input, right? And then here is your differential equation solution down here. And we have our homogeneous, c1 e to the x plus c2 e to the 4x, right? That was the homogeneous. Everyone good with that? And then here is the particular solution. And so you see that, first of all, we guessed the correct particular solution, right? Because we have x e to the 4x right here, right? We have the x e to the 4x term, and then we have the x squared e to the 4x term. So we guessed the right particular solution, and then that just gives you the constants that you really should get. So the idea then is you shouldn't really be missing any problems on like homework because you can always check yourself. The other side to it is then if you just put the answer down without showing any work, you're going to get a 0 because I'm just going to assume you copied from Wolfram alpha. So that's kind of the trade-off there. But it's always nice to like be able to check yourself on your math, especially since this is really computationally tedious. The other thing is that this is also a good tool for then if you're trying to study for the midterm, you just want to have practice with differential equations. You can literally just go to the textbook and just do any like problem from the textbook, right? And then you can just plug it in here to make sure you got the right answer. So that's really nice. Okay? All right. I'm going to try to squeeze in another example then in the last 5 minutes. So this is what you guys did yesterday. And oh boy. And this is by far people's least favorite thing to do. It's called complex value trial solutions. Okay, and the idea is the following, right? What happens if f of x is e to the ax sine bx or e to the ax cosine bx? if you use annihilators, okay, go back to our annihilator table, e to the ax sine bx or e to the ax cosine bx, right? Look at what we have to guess. We have yp of x is e to the ax like plus some like sum here, right? So remember, we have to take derivatives of this thing, and if you also had an x to the k term, you're going to end up taking like triple product rule, all right, which is super not ideal. So what we can do instead is the following. We can use a complex value trial solution. So for example, if you have, is this the one I wanted to do? I had one I wanted to do. 1 second. Okay, I guess this is the only one I can do. So let's say I have the following. Y double prime minus 2y prime plus 5y is equal to 8 e to the x sine 2x. Okay. So what you have to do then is the following. So step 1 is always the homogeneous. And so, okay, so this is, so you can't factor this guy. And so you'll get d is equal to 2 plus or minus the square root of 4 minus 20 all over 2. So this is 1 plus or minus 2i. So you'll get then yh is c1 e to the x cosine 2x plus c2 e to the x sine 2x. And you see this really nice, nasty thing going on where you have the right-hand side is equal to something in your homogeneous. That's never a good sign. So step 2 is to guess yp of x. And here's the idea. 8 e to the x sine 2x. Where does this come from? Well, here you can see that a is equal to 1 and b is equal to 2. Right? Because we always call this guy a and we always call this guy b. So this means that it comes from e, right, to the 1 plus 2ix. All right, because remember, this was like last week where we broke down e to the a plus bix into a sine and a cosine term. All right, so now we're going backwards. We're going from our sine and cosine terms, and we're going back to this e term. Okay? And the idea is the following. Since it comes from e to the 1 plus 2ix, all right, we then want to guess yp of x is equal to some constant, let's say a naught, times e to the 1 plus 2ix. What's the problem with guessing 1 plus 2i, with guessing this though? Yeah, it's equal to the root in part A, right? So what's the fix there?
Throw an X in?
Yeah, we throw an x in, right? So 1 plus 2i is in here once, right? 1 plus 2i and 1 plus 2i. Okay. So to fix this, then we need to multiply this guy by x. So really, we need to guess yp of x is equal to a naught x e to the 1 plus 2ix. Okay, and the idea is you proceed normally with your derivatives. So step 3 is going to be I'm running out of time, but essentially, right, you get yp prime of x is equal to a e to the 1 plus 2ix plus 1 plus 2I a x to the e to the 1 plus 2ix. All right, so you just proceed normally. The only annoying thing, and this is why like students like really hate this, is you have to deal with that complex number. All right, but it's actually better than the alternative of guessing what you did above, because you would have triple product rule. So anyways, so this is the idea. This is what you'll guess. This might show, I think this was on the homework, so this is why I want to cover it real quick. You'll get, do I even have the other page for this? Oh, cool. So you'll get the following. So you'll get something that looks like the following. You'll get yp of x. So once you solve for yp double prime of x is equal to whatever, you take your derivatives. You'll end up getting yp of x is equal to negative 2I x e to the x cosine 2x plus 2x e to the x sine 2x. All right, so this is what you'll get for your particular solution. And then here's the part that also doesn't sit well with students. F of x is a sine term, right? If you go back up here, right, f of x is a sine term. It's 8e to the x sine 2x. All right? This means we choose the imaginary solution. What does that mean? Well, yp of x, here's an imaginary solution. It has an I. Right? So this is the imaginary solution. And this, on the right-hand side, this is the real solution. So if it were cosine, you would choose the real. All right, but since it's the imaginary solution, we choose the since f of x is sine, we choose the imaginary solution. So our correct choice of yp of x is equal to negative 2x e to the x cosine 2x. And so notice that I dropped the I, all right, when we choose our solution. So then this is the correct choice of yp, and then you add it to your homogeneous and you're done. Okay, so again, f of x is imaginary, f of x is sine, right? It's 8 e to the x sine 2x, so it's a sine term. We choose the imaginary solution, and then once we choose the imaginary solution, we drop the I. And then so we have negative 2x e to the x cosine 2x. And so that's the solution that we want for a particular. The reason why we do this is because if you work out all the algebra, it actually like works out this way. So like just if you don't want to do the tedious computations, you don't have to. Just follow these two rules of thumb and you'll be fine. Okay, that's all for this week. You should be able to do the homework. I'll probably do out one of these examples. So recitation next week. I'm going to be here on Wednesday, so I'm going to be holding recitation next Wednesday morning. So if you want to come, so Wednesday's the Friday schedule, so I'm going to be in this room. So 8 a.m., 9 a.m., I'm going to be here. If no one shows up, I'm going to talk to myself. I'm going to just do problems. I'm going to record it. But feel free to show up. It's because we're going at a pretty slow pace, so I feel like we need as many recitations as we can to like introduce the other methods of solving diffie-Qs. So, all right. That should be enough for homework this week. This recording will be posted in about a few hours. So.
Can it ever be not sine or cosine?
What?
Can it ever be not sine or cosine?
Yeah, it can be like tangent secant.
Okay, so it has to be a trig function.
Wait, what do you mean? Like for the complex value trial?
For f of x, does it have to be
You're pretty much always going to be given sine and cosine, but it can it can be something else. Because there's other methods we can have where we can solve for the fact that the right-hand side is not a sine or a cosine term, right? But when you have sine or cosine terms, this is like the go-to. Although complex value trial and annihilators, they're like the most rudimentary, so they're like I hate using them.
We should still know how to use both of them for the exam.
You should know how to use them for the exam.